Excellent. I'll just marking the roll as we go, so I'll just note down those people who have just arrived. Okay. So single phase transformer. So we've moved on from lighting. So this whole module is primarily based around lighting and transformers. Don't ask me why those two things go together. It doesn't make much sense to me, but here we are. So what is a transformer? Now we've talked about transformers a little bit in terms of the concept. I think most of us understand that they exist. I suppose we haven't gone into much detail about what they are, what they do. Does anyone want to throw out a guess or remember from previous discussions primarily what is a transformer for? What do we use it for? You can throw your microphones on and just say something if you want to. No, nothing at all. Nobody has any idea. Okay. So what it says here is a transformer is a static device that transfers energy from one circuit to another by electromagnetic induction. So really what that means is the basic premise of a transformer is that it enables us to, as it says there, transfer energy from one circuit to another. Now there's an implication there that one side of the transformer is then a separate circuit from the other, and that is true. The thing that makes a transformer, or that enables us to use the transformer to do the things that we want to do with it, is the fact that we have input into a transformer and we have output from a transformer, but the input and the output are not electrically connected. Well, they're not physically connected. They're not touching in an electrical sense. So whilst we have an electrical output, we can use power off the output of a transformer. It does not touch the input. There is no direct circuit from the input side to the output. If I put a multimeter from the input of my transformer to the output, I will get no reading. There is no continuity between them. The most important use of a transformer is to change voltage. When I say change voltage, that means we can use a transformer to either step our voltage up or down, which means I can put a certain value of voltage in, and then I can get a different voltage out of it. And that's where the name comes from, really. That's transforming the voltage from one value to another value. Common application to what we talked about yesterday, 12-volt lighting, right? Those 12-volt MR16 spotlights. So we have a little transformer that sits in the ceiling. I put 230 volts into that, and I can get 12 volts out of it. So it's changing the 230 volts down to 12 volts. Now, how does it work? Oh. Here's a diagram of a transformer, a very simple diagram of a transformer, which helps to illustrate how physically that works. So we got a primary winding and a secondary winding labeled there. Primary winding is voltage input, so I connect that to a source of supply. Secondary winding is voltage output, so I connect that to a load. We can see that the primary winding there is a big coil of wire. What happens when I connect a voltage to a big coil of wire? It's one word, starts with M. Nice, magnetic field. Thank you, Raymond. Appreciate your participation. So we're going to get a magnetic field, and we have in here a laminated iron core. So we've got the copper coil is wound around that core. So we're going to get a magnetic field generated when we put a voltage onto that primary winding. Now, much like we have with generator and motor, generator and a motor are the same things. The principle is the same, but except in one case I'm going to move the rotor and I get power out. That's a generator. In the other case, I put power in and movement happens. Something similar is happening inside a transformer when I put a magnetic field or place a voltage on the primary winding and therefore create that magnetic field, which is amplified by the laminated iron core, or at least it's transmitted through the iron core. Then having the secondary winding inside that magnetic field then induces a voltage into that winding. It's a little bit more complicated than that. I need a changing magnetic field because it's actually the process of, again, like we kind of talked about yesterday with our fluorescent, right? That remember we said that as we build the magnetic field in the ballast, and then when we turn it off and we take it away, that magnetic field collapses and it transmits its energy back into the circuit. Something similar is happening to here because when I put an AC voltage on the primary, as that voltage goes up and down, changes, and then kind of turning itself off, right? Because it's going to zero. It's that changing magnetic field that's inducing the voltage into the secondary winding. The physics of how that works, I guess magic. Your guess is as good as mine. I don't know the intimate details of what's happening with electrons. Why are they being influenced in these ways? I don't know, but we don't really need to know. It is what it is. So you'll have to believe me, magic. We put a changing and alternating voltage onto one side of the transformer, and that will induce a voltage on the other side of the transformer. That is the most important concept that we need to understand. And really, all we're doing here is we're taking one coil, putting a voltage on it. We have a second coil that is mounted physically. It has to be physically close to the first coil. It has to be within the magnetic field of the first coil, and we're going to get an induced voltage. The only reason it's important to understand that it's that changing magnetic field, that changing voltage that's going to help induce the voltage into the secondary, is that a transformer will therefore logically follows only work on an AC supply. If I put a DC supply onto a winding like this or onto a transformer, it will generate a magnetic field, but there will not be a secondary or there will not be a voltage induced into the secondary winding, because I need to have that changing magnetic field. That collapsing magnetic field is what is going to induce that voltage. Am I making sense so far? Cool, good. Yeah, I always get a little bit caught up talking about transformers because I feel like I need to explain. I feel like I'm doing everybody a disservice if I don't get into the nitty-gritty of why. Why does that happen? Because it kind of does. There's a few things in the electrical world that even in the 20 years I've been doing this still kind of seem like magic to me. And this is one of them. I don't get it. I really don't. Like I could probably tell you the words of how it works, but to be honest, I don't think deep in my brain I really understand that. There's still an aspect of that that just seems like magic. And I think we should just give in to the magic and we'll just let it be magic. We have a magnetic field, a changing magnetic field because we put a voltage onto that primary winding, and that changing magnetic field is then transmitted to the secondary winding and a voltage is induced upon it. So here we go. It gives us two things really. One is the ability to change voltage. We'll look at that next. It's very simple how it does that. Again, it's a little bit magic, but the words are simple. And then the second one is it gives us an isolated supply. So as you can see from this very simple diagram, is there's no physical electrical connection from the primary to the secondary. And that means that the secondary winding, therefore, although there is voltage there, electrically it is isolated from the primary and anything else the primary is connected to, which would be the national grid, right? The power infrastructure. We are physically and literally not connected to it, which will become useful later because it makes a difference for safety and earthing and stuff like that. Oh God, okay, we're going to have one of those slideshows that has all the animations. This will be fun. Okay, so let's have a look at the construction of our transformer then. Here is our iron core. This one has 3 limbs. Actually, let me just... there we go. So what you can kind of make out for from this is that iron core itself is not it's not a single piece. We've kind of mentioned this before that when we have an induced voltage, or rather when we have a magnetic field in a coil from applying a voltage, and we have an iron core there to help us magnify and use that magnetic field, the iron core itself can act as the secondary of a transformer. So we'll have a current or a voltage induced into it because it's a conductor. It's a conductor sitting in a changing magnetic field, just like our secondary winding is. So the iron core itself will act as a type of secondary winding and have a voltage induced into it. If we have the iron core as a single piece, then we're going to have a large core coil, if you like, sitting in that magnetic field with a high cross-sectional area because it's one single piece of metal, and therefore very low resistance. And so quite a bit of current will be induced into that, and we'll get what we call eddy currents. So we're going to have current flowing inside that iron core. It will create heat, and it also reduces the efficiency of the transformer. It reduces the efficiency of the transformer because we're burning energy with current flowing around in circles inside the iron core. So one of the ways we defeat that is the iron core is split into laminations, as you can see in that picture there. So that's like thinly stacked pieces of steel that are insulated from each other. So that is going to help us reduce what we'd call iron losses. They're called iron losses because those are the losses that we get in the iron core. So you can see in this diagram here, the construction is those sliced, if you like, or thin steel plates that are insulated from each other, and that makes up our iron core. The reason this works is because the insulation presents no barrier to the magnetism. So the overall magnetism in the iron core will remain the same, or the efficiency of the iron core to do its job as an iron core is not changed by by insulating the steel sheets from each other. But electrically, it does change things, because now we've got, instead of one big chunk of steel, we've got a whole bunch of little ones, which is going to reduce the ability for current to move through. Well, it removes the ability for current to move through that coil. It can only move through each individual steel laminate. So it still works as a magnetic amplifier, but it does not work as a conductor of electricity. So that's how this works. So in this case here, both the primary and secondary windings are placed over the center limb, so they'll be wound around the center limb, which it works, still works, right, as long as those are insulated from each other, so it's be insulated wire. But I can have the primary and the secondary, one wound over the top of the other, or in fact wound together. It doesn't make any difference, and the iron core will still do its job to contain and amplify the magnetic field generated in the primary when I put a voltage in there, and then the secondary core is sitting within that magnetic field, so voltage will be induced into it. They don't have to be physically separate. They could actually be interwound, as long as I say, as long as they're electrically insulated from each other. It actually makes no difference. The steel core of a transformer is made of magnetically soft transformer steel. So magnetically soft means easily magnetized and easily demagnetized. How that works is to do with the physical composition of the steel itself. I think it's higher in iron and lower in carbon, perhaps. That makes it more magnetically soft. The core is constructed of alternately interleaving very thin laminations of steel. So we talked about the laminations there. So alternately interleaving means like this, stacking them where they overlap like that. This enables the windings to be wound onto a bobbin and then simply slid onto the steel before being bolted together. So this is something about the construction, the physical way that we build the transformer. If you think about, if we go back to that picture that we were just looking at, so you can see that it says alternately, which means we could pull that thing apart. There'd be a top half and a bottom half. If I made this one as one single piece, then I would have to physically wind the coils on through the holes in the middle, right? Whereas if I make it like this, then I can wind the coils separately, slide it onto the bottom part of the core, and then slide the top part of the core over top of it. So it just makes it easier to physically build that. The very thin lamination, so 0.2 to 0.35 millimeters, so very small, are stamped from a sheet and insulated from each other by a fine layer of varnish. And it's, as I talked about before, that reduces the iron losses. To reduce the unwanted electrical current, the eddy currents set up in the conductive steel core due to it being in the presence of a changing magnetic flux. Yeah, that's what the laminations are for, as we discussed. Okay. Are we happy with that? Any questions on that one so far? I know the slideshow is going straight into the construction of the different types, which probably seems quite confusing, since this is our first introduction really to the concept of a transformer. But as we go through it, it will start to become clearer, hopefully. Questions? No, we're happy. Okay. This is a core type transformer. It has 2 limbs rather than 3. Primary and secondary windings are distributed on both limbs. Half the primary and half the secondary turns are wound onto one limb. And half the primary and half the secondary turns are wound on the other limb. So same as I was talking about before, we can have them wound together. So I have half of the primary wound onto one limb and then across to the other limb, and then maybe the second one over the top of that one. They're usually wound concentrically. Double wound transformers. The vertical portions of the laminated iron core are called limbs. The top and bottom portions are called yokes. The two windings are placed on the limbs. Oh, these animations are horrible. Okay, let me go back a bit. Yeah, so these are our limbs here, the vertical portions, and then the top and bottom are the yoke. So I wind the windings onto the vertical portions. Those are called the limbs. And yep, that's it. The primary winding is connected to the supply, so that's where I put my voltage on. Secondary winding is connected to the load, so that's my output side going out to whatever it is I'm powering. When the windings are electrically separate, as we've talked about, we have two windings that are not connected to each other electrically. This is called a double wound transformer. It's a double wound transformer because I have two separate windings that are insulated from each other. They have no electrical connection between them. So the operating principle, when the current flows through the primary winding, it sets up a magnetic flux around that primary winding. Right, that makes sense. We went through that. The magnetic flux takes the path of least reluctance, which is the transformer's iron core. Reluctance in this context is a word that it means the same as resistance, but it's specific to magnetism. So magnetism in this context wants to flow much like electricity flows in a wire. The flux will follow the path of the iron core. The secondary winding has an EMF induced into it by the flux in the iron core. So the flux that is being created in the primary winding and then transmitted through the iron core will induce a voltage, EMF, into the secondary winding. EMF is only induced in a conductor when the flux coupling that conductor is changing in strength. So as I said before, we have to have a changing magnetic field in order to induce the voltage into the secondary. Why? Magic. But it's true. So that tells us then, as I said before, our transformer is only going to work on AC. It will not work on DC because DC will not give us a changing magnetic field. It will give us a constant magnetic field. When connected to an AC supply, the direction and magnitude of the current is always changing. So an EMF is always available at the secondary terminals, because we have that sine wave, positive, negative magnetic field, or positive, negative voltage on the primary, and therefore it's giving a changing magnetic field. So we always get a voltage at the secondary. Here is, these are, what do we call it? Symbols, wiring symbols. So if I was drawing a wiring diagram, this is the symbol that it would look like. The wavy line represents the coils, and then the two straight lines between them represents the iron core, and then obviously I have my power in on one side, power out on the other. In a line diagram, you would draw the picture that we have at the bottom, the two interlocking circles that represents a transformer. Okay, transformer calculations. All right, this is where it gets fun. So I said before that our voltage can be changed in a transformer, right? I can get a different voltage out than the voltage that I put in. And that is governed by the number of turns. This might sound ridiculous in the sense that it's too easy or too simple. Nevertheless, it is true. If we look at this equation here, the voltage on the primary divided by the voltage on the secondary is equal to the turns on the primary divided by the turns on the secondary. So our most common usage of this equation would be to work out how many turns I need to get a certain voltage change from one to the other. Or if I've got a certain number of turns, what are my output voltage going to be? So if I said I had 100 volts on the input, that would be my primary voltage. And let's say I have 100 turns. And when I say turns, that means the physical number of coils in my coil. So if I coil my primary winding around the core 100 times, it's 100 loops is my number of turns. So 100 volts on the primary and 100 turns on the primary. If I put then say 10 turns on the secondary, V primary is 100 equals N primary over N secondary, 100 over 10, which means the voltage on my secondary must also be 10. That is our transformer ratio. If I have 100 turns on the primary and 10 turns on the secondary, then my secondary voltage will be 10 times less than my primary voltage. It's exactly that simple. If I had a transformer that I was going to connect to 230 volts and I had 230 volts, 230 turns on the primary, and then I put 12 turns on the secondary, 230 volts in to 230 turns, it's going to give me 12 volts out on 12 turns on the secondary. But it's the ratio that's important, not the exact number. So if I had 230 volts into a primary winding that had 23 turns, and then I had one turn on the output, well, 230 divided by something equals 23 over 1, it would be 10. So 230 volts into a winding that has 23 turns will give me 10 volts on the output if I had one turn on the output. Does that make sense? Okay. Okay, let me think for a minute, Ollie. Appreciate that. So we'll give me a second to think if I can think of an analogy that will make this sound a little bit simpler. Okay, so well, I guess the simplest way to explain it is exactly as this formula says here. The ratio of turns, and remember when I talk about turns, I'm just talking about the number of loops or number of coils on the winding. The ratio of turns from primary to secondary will be equal to the ratio of turns, let me start again. The ratio of turns from primary to secondary will be the same as the ratio of voltage from the primary to the secondary. So if I have 10 times as many turns on the primary as I do on the secondary, then the primary voltage will be 10 times higher than the secondary voltage. Or another way to put that would be if I have 10 times as many turns on the primary as I do on the secondary, then the secondary voltage will be 10 times lower than the primary voltage. And that is the way that I can transform the voltage down. If I want 10 times less voltage from primary to secondary, so if I want to change 230 volts to 23 volts, then I just need to make sure I have 10 times as many turns on the primary as I do on the secondary. If I wanted to change the voltage up, then we'll use the exact same equation. It's just going to work the opposite way. If I want a higher voltage, let's say I wanted 10 times as many volts out on the secondary as I'm putting in on the primary, then I have 10 times as many turns on the secondary as I do on the primary. And it doesn't matter how many turns I have, it's just the ratio. So if I want to transform my voltage upwards by 10 times, I want to get 10 times as many volts out as I put in, then I could put 1 turn on the primary and 10 on the secondary. I could put 10 on the primary and 100 on the secondary. I could put 100 on the primary and 1,000 on the secondary. Either way, that ratio is going to be 10 to 1. So whatever voltage I then put into the primary on that example, I will get 10 times the voltage output on the other side. Which is good. Like it takes a little bit to wrap your head around that, but when you think about it, it's really simple, right? It's that simple. In terms of constructing a transformer, if I had an iron core and lots of wire, then I can exactly predict how many volts I'm going to get out of it by making sure that I set the ratio of turns from one side to the other to whatever I want. If I want it 10 times, 10 times as many turns. If I want it 20 times, 20 times as many turns. If I want to go up in voltage, then I need to have more turns on the secondary than the primary. If I want to go down in voltage, I want fewer turns on the secondary than I have on the primary. Does it make more sense now? Okay, cool. Now, Nathan, is there any benefit in having more turns while keeping the ratio the same? That's an excellent question, because I was kind of thinking that myself as I was saying that. I could go 1 turn to 10 or 10 to 100 or 100 to 1,000 and I'll get the same ratio. And then as I'm saying that in my head, I'm thinking, I wonder if that's important, whether I use 1 or 10 or 100 turns. And I don't know. I don't actually know the answer to that. In terms of the voltage input and output, well, clearly no. The answer is no, because the equation remains the same. It doesn't make any difference. Would the transformer operate more efficiently if we had more turns? Yeah, I'm genuinely not sure, to be honest. I'm genuinely not sure. Perhaps we will discover that as we go further. If not, I might look it up later. I apologize, I cannot answer your question directly. It's a good question, though. Yeah, sorry, mate. We'll find the answer to that. Okay. So the next step in this equation then is the ratio of the primary to secondary current is inversely proportional to the ratio of primary to secondary turns. So that means current is going to behave the opposite to voltage. If I have more turns on the primary than the secondary, that means that my voltage will be reduced, but my current will increase. If I have fewer turns on the secondary compared to the primary, my voltage will reduce. Or is that what I just said? If I have more turns on the secondary than the primary, my voltage will increase. More turns on the secondary than the primary, so my output voltage will be higher, but the input current will be lower, or the output current will be lower than the input current. Now, I know that probably on its face sounds crazy. Here's the formula here. Current on the primary divided by current on the secondary is equal to the number of turns on the secondary divided by the number of turns on the primary, which means we're flipping that equation over compared to the voltage one. But the easiest way to remember this, or the easiest way to understand this, is that the power input on the primary and the power output on the secondary will be the same. So if I'm putting 1,000 watts into the primary, I'm going to get 1,000 watts. Well, actually, no, scratch that. If I draw 1,000 watts from the secondary, then I must draw 1,000 watts from the primary. Which means that if my voltage changes, remember that power is voltage times current. So if my voltage changes, my current also changes. If my voltage goes up, my current goes down. If my current goes up, If my voltage goes down, current goes up. Power on either side will be the same. So an example of this, actually, let me see if I've got a whiteboard here. Okay, can everyone see my whiteboard here? Okay, let me try this. Let's see if this works. It's going to be atrocious trying to draw with a mouse, but I'll try my best. Let's have a look. So if we said then that number of turns on the primary divided by the number of turns on the secondary is equal to voltage on the primary divided by voltage on the secondary. Then, as I said, if I put 100 turns on the primary and 10 turns on the secondary, then that will equal, and let's say I've got 230 volt input on the primary. Don't see the whiteboard. So some people can see the whiteboard and some people can't. Reload the call. Try reloading the call. Are you saying I should reload the call or they should reload the call? Rejoin the call. Okay, try leaving and jumping back in if you can't see it, team. Cool. Yeah, good job, Tanner. Thank you, mate. Okay. So we're saying the number of turns on the primary divided by number of turns on the secondary is equal to the voltage on the primary divided by voltage on the secondary. So this is the first equation we looked at. If I have 100 volts, if I've got 100 turns on the primary of my transformer and 10 turns on the secondary of my transformer, and I apply 230 volts to the primary, what will my secondary voltage be? Well, it's a little bit of transposition there, but let's make it simple. 100 divided by 10 is 10. So 230 divided by what is 10? It must be 23. So that means my secondary voltage will be 23 volts. There we go. Does that make sense? Cool. So now our second equation was the opposite of this. Our second equation said IS, so current on the secondary, divided by current on the primary is equal to number of turns on the primary divided by number of turns on the secondary. So on the voltage, we had primary on the top of both sides and secondary on the bottom. But this one we've got primary current is on the bottom, primary turns is on the top. Secondary current is on the bottom. Secondary current's on the top. Secondary turns is on the bottom. So in this equation, if I use the same transformer, so I've got 100 turns on the primary, and 10 turns on the secondary, and my current that I'm drawing from the, let's say the current I'm drawing from the secondary side is 1 amp, then what would my primary current be? Well, we can see from this equation that the number of turns from primary to secondary again is 10 times, but because the secondary and primary are reversed in this equation, that means that hang on, let me think for a second. I'm confusing myself now. Yeah, okay, right, I've got it. Yeah, so that means that the primary current must be 10 times less than the secondary current, because my turns ratio is 10 times less, which means that my primary current will equal 0.1 amps. So drawing 1 amp off the secondary in the situation where my secondary windings are 10 times less than the primary windings means that my current on the primary will be 10 times less. Now, as I said, this relates directly to power. Even though the voltage and current are changing 10 times up, 10 times down, and they're opposite to each other, what that means is, and this is, and I find this is the easiest way to keep this straight in my head, is that the power on each side would be the same. Now, fastest way, we can really easily, we can demonstrate that, right? So we've got 230 volts that we put onto the primary with 0.1 amps. So the power on the primary must be 230 volts times 0.1, right? Because that's my current that we just calculated is on the primary. 230 times 0.1, which will equal 23 watts. Oh no, my mouse is getting out of control. So that tells us then 230 volts times 0.1 amps on the primary side gives us 23 watts on the primary side. Now, if we look at the secondary side, our output voltage was 23 volts. We calculated that here, calculated that first. So power on the secondary that's ugly. Power on the secondary is equal to the secondary voltage was 23 times secondary current, which was 1, which equals 23 watts. So if we know that the wattage must remain the same from one side of the transformer to the other, then it's much easier to understand that ratio in terms of turns, volts, and current, right? So that means then that whatever ratio that the voltage increases or decreases, the current must increase or decrease by the same ratio, except in the opposite direction. So if my voltage goes down times 10, then my current goes up times 10. If my voltage goes up times 10, my current goes down times 10. And then the power from one side to the other would remain the same. Does that make sense? I hope that makes sense. It's simple maths, but it's a complicated concept, I think. It's a bit of a pain in the ass. Okay, so now I want you to think for a bit. Sing out the answer if you can figure it out. But this mathematics that we just did here and these principles explain why we transmit voltages or we transmit electricity at such high voltages, right? So we know that power lines, for example, we use 11,000 volts, 33,000 volts, 220,000 volts. We use these really high voltages, so we're all aware of that, right? So what that means is power is generated from the power station at whatever voltage it is. I don't actually know whether there's a standard in New Zealand for a certain voltage that we generate power at. But it's kind of irrelevant to our purposes because as soon as it's coming out of the power station, we're going to have big ass transformers there that are changing that voltage upwards. And then it transmits that high voltage along the power lines until it gets to a point where we want to use it. And then we have another transformer there to bring that down to the voltage that we want in our homes, for example. So there'd be a transformer somewhere in your street or in the next street or something like that that's transforming that higher transmission voltage. Now that transmission voltage varies. We use different voltages in different places, but that doesn't matter. The important point is that that high transmission voltage is transformed back down to 230 volts to feed to our houses or to feed to whatever. So as I said, I don't know what the voltage coming out of the power station is, but let's say it's 230 volts. It doesn't matter. Let's say 230 volts out of the power station. We transform that up to 200,000 volts. We send that 200,000 volts down the power lines all the way from the power station to your house. And there's a transformer out in the street somewhere that changes that 200,000 volts back down to 230, and it comes into your house. Now, the obvious question is there is why? What difference does it make? Why do I want to transmit that voltage at 200,000 volts if it's being generated at 230 and used at 230? Well, this calculation here, what we have written on our little whiteboard here, tells us why. This gives us the answer. If I've given enough information for anyone to have a stab at what that means? Why does this calculation tell us the answer as to why we want to transmit our power at very high voltages? Well, someone must have a guess. Okay, so let's go another step then. If I'm looking at what we've got written here, understand those ratios of voltage and current, which means that the power on both sides of my transformer always remains the same. So if I'm increasing the voltage, I'm doing what to the current then? Low current, nice. Yeah, you're on the right track, Ollie. You just went the wrong way around. So Bailey and Jade are onto it here. So as I increase that voltage, I'm going to reduce the current. Now, what do we know about circuits in terms of high voltage and high current? If I have a high voltage on a circuit, what does that affect? What is our primary thing that is affected by voltage? Or what's our main construction consideration for managing voltage? It's probably a weird way to word the question, but Not so much resistance. When we use a high voltage meter, when we use our insulation resistance meter, why do we use that high voltage? To stress the resistance? Is that the right word that you were looking for? Check leakage. Yeah. So we're. Oh wait, Jade's typing. I'll wait for Jade. No. So when we use an insulation tester, we use that high voltage. Okay. We're stressing the insulation, right? Because the higher the voltage, the more likely it is to break down the insulation. But the conductor itself doesn't really care. The voltage that you put on a conductor doesn't do anything. It doesn't make any difference to the conductor, but it makes a difference to the insulation, right? If I just had two conductors like this, you guys can still see my video, right? You can see the whiteboard and the video. Yeah, okay. So if I have two conductors like this, and I put a voltage on there, if I've got an air gap, if I've got a big enough air gap, the air will act as insulator, right? But if I started putting higher and higher voltage on there, and I left the gap the same, at some point that voltage is going to be high enough to jump across. It's going to break down that insulation and conduct between my two conductors. Agree? Yeah, okay, good. Someone agreed. Jade agrees. But the voltage that I put on there doesn't have much impact on the conductor itself, just on that insulation. So as long as I raise that voltage, I separate the conductors apart more and more, then the insulation integrity will remain. So I would just need to, if I was using air as the insulator, just need to make sure I have a big enough air gap between the conductors, because the air is my insulator. So as I increase the gap, I'm increasing my insulation levels. So when I'm using a very high voltage, such as for power lines, the impact of that voltage is I need to have a greater insulation, which means I just need to have a bigger gap between the conductors, which in terms of cost or the way I construct it, physically building a power line, it doesn't make much difference, right? Whether those conductors are 20 centimeters apart or 2 meters apart, it doesn't make a huge difference to how I construct it. Agree? Does that make sense? Yep, okay. Thumbs up, cool. However, if we start thinking about current, what's going to change it in my circuit if I start to increase the current? Or what do I need to do in my circuit in order to mitigate very high levels of current? Bigger cables, nice. Is that what you were going to say as well, Jade? I see you're typing. Good. Yep. So it means that if I have a higher current, I need bigger cables, right? Because we're going to get that heat occurring in the cable, and at some point the current will be so high that it will burn out the cable. So the more I increase my current, the more I've got to have bigger cables. So now, knowing all of that, well, yeah, okay, yeah, resistance, sure. Okay, yeah, well, in the context of all of that, now your answer makes a bit more sense to me, Bailey. So, so yeah, in the context of all of that, we should now be able to figure out why. Why do I want to transmit my power at very high voltages? Okay, come on, someone answer. Okay, no one's going to answer. All right, I guess it's me. So, if I increase my voltage dramatically, then I'm going to reduce the current. Uh, that means two things. Higher voltage means I need more insulation, but the insulation is air. It doesn't cost me anything. I just got to make my wires further apart. But that higher voltage, because of this maths that we just looked at, means that my current is going to go down. Current going down means I don't need as big a cable. I can use smaller cables to transmit the same amount of power at a higher voltage. Does that make sense to everyone? Cool, cool. So that the heart of why we use transformers in our power distribution system throughout New Zealand. Why we need those high voltages, or why we use those high voltages, because it's a cost saving message, right? Yeah, yeah. So you nailed it there, Raymond. That it's going to be better over uh, longer distances because I can transmit much higher levels of power. And when I say power, in this case, I don't mean necessarily electricity in general. I mean power as in how many watts. I can transmit much bigger power levels with smaller cables. So it costs me shitloads less. Now, if I was generating power at 230 volts and then transmitting it at 230 volts out to every house, every business, every building in New Zealand, we might need cables, like our cables might be 6 feet thick, 10 feet thick. I actually have no idea. I've never thought about it, but they'd be enormous, right? They'd be absolutely massive. We saw when we did our maximum demand calculations that even going from up to say 100 amps, we're looking at 50 mil cables. So think about now if we had to transmit power 1,000 amps, 10,000 amps, 100,000 amps, the cable sizes would be unbelievable. So we transmit our power at a higher voltage in order to reduce the current, and we use transformers to do that. So the question there, Tanner. Well, the cable size will still be determined by the current drawn. As you can imagine, the current drawn right at the start is going to be more than current drawn in my street because as it gets further and further away from the power station, it's going to branch off to various things. So the current will be less and less. Hence, we'll probably use our highest voltage at the power station, and then as it's coming closer to our individual houses, as it splits off to, let's say, power is generated at the power station for 2 different cities. As it splits between those cities, I only need half the amount. I can reduce the voltage a little bit or make smaller cables, and then as it gets to each individual street, the demand will be less and less. But I mean, if you look at your average power line, I mean, the cables they're not that big, right? They're certainly, like, say, thinner than my wrist, probably bigger than my thumb, thinner than my wrist. This is about as close to the answer that I can give you. But they don't have to be massive. And we could easily see, just knowing what we know about maximum demand and stuff like that, that, if we were transmitting at 230 volts, uh, clearly, clearly those cables would be nowhere near big enough. And so the whole transmission system would be so much more expensive because we'd have to run these enormous cables everywhere. And then, there'd be all sorts of other problems, like how do you hang them if they'll be that big, or do we have to put them in the ground and, all of that kind of stuff. Uh, so transformers give us the ability to minimize the size of our transmission cables by increasing the voltage and therefore reducing the current. That's pretty good. That's right, that's 90% of transformers done. That's the important shit. So if you can get your head around that, we've gone a long way. Interestingly, so back in the day, this is somewhat off topic, but not too far off topic. Back in the day, when electricity, not so much when it was first invented, but when it was first being utilized for commercial purposes, as in being generated and transmitted out to houses and businesses. So this is when people started getting electric lights and stuff like that. There were two competing theories, and one was proposed by Thomas Edison, and one was proposed by Nikola Tesla. Now, Tesla obviously is a bit of he's become more and more famous over the years, and most of you guys, I would guess, would be familiar with Tesla's name, in the sense that he was an innovator. He was the good guy, and Thomas Edison was the bad guy, which is maybe not completely true. I think over probably the last 20 years or so, Tesla's reputation has increased, where people have perhaps realized that his innovations were maybe better or more valuable than people thought at the time. But that's neither here nor there. Nevertheless, Thomas Edison proposed that we used DC. So his power distribution system was based on DC, and Tesla's system was based on AC. Now, obviously, AC won because we have used AC power today. But again, if we go back to the stuff that we've now discussed and what we've just learned about power transmission, can anyone tell me why AC won in the end? No one's brave enough to answer that one. What did we say about transformers using AC and DC? There we go. Nathan's got it. Yep, because a transformer uses AC. You can't. A transformer will not work on DC, which means that if our power distribution system was based on DC, then we would have to generate the power. We'd have to generate the electricity at the same voltage that we're going to use it. So we would have to generate the electricity and transmit the electricity at the same voltage that we're going to use it, which obviously doesn't work in the context that we're just talking about here, right? If we had a big power station and then we're going to generate all the power for Auckland City, then and we're transmitting that power at the same voltage as we want to use it, which will be 230 volts when it gets to your house, right? Then we will have to transmit the power at 230 volts. We'd have to use enormous cables. Now, Thomas Edison's idea, or his concept for a generation system, did not include having enormous, massive cables and transmitting everything at that voltage. His system was based around the idea of having a lot of small generating facilities. So you might have a generator on every street or something like that, which probably sounded fine in the context of the day. That maybe if you'd have to have your building specially fitted for electricity, and none of your neighbors would have electricity, maybe. So it's not a stretch then to think, well, when you get electricity fitted to your house, you need to have your own generator. Or when every house in the street decides they want to get electricity, then everyone bands together and pays for the generator that would power the street. Now, yeah, at the time that probably seemed quite reasonable. Looking back from the view we have now, that they probably didn't realize that the future of electricity was that every single house, every building, everywhere had electricity. That our entire the world that we live in is completely permeated by electric wires everywhere, right? Street lighting, power to our houses, all of that sort of stuff. Yeah, Tesla knew. That's right. Tesla's the good guy in this situation. I don't know whether he, had that view or what, but he was the proponent of AC. Edison wanted DC. So yeah, clearly looking back, that DC system wouldn't have worked. We wouldn't be able to have big, efficient generating facilities. We would have to have small generators everywhere in order to be able to transmit power at the same voltage that it's used. Well, maybe not Bluetooth. He had an idea for uh, wireless transmission of power, but I think that one was a bit pie in the sky. It's a bit bullshit. Unfortunately, these days, because Tesla had a lot of ideas, and if you look at this one, right, this is a good example of where he had a different view of the future. So his idea works in the modern day way better than Edison's would have. At the time, though, Edison's idea probably sounded quite reasonable. So, with the benefit of history, we've realized actually Tesla was so much more right than Edison was. It's not even funny. So then that has the effect of, in our mind, making us think that Tesla's ideas were actually way ahead of his time. So every idea that he had that might have been rubbish at the time is probably just because we haven't caught up with his ideas yet. So then you get people who think everything that he said is some sort of prediction of the future. And if it doesn't make sense to us, it's because we haven't got there yet. So ideas about wireless transmission of power and so on and so forth. And I don't think that's necessarily true. Not all of his ideas were amazing. But look, I don't want to spend the day talking about Tesla. Just put your hand up there, Solar. If you have a question, or you're just pushing this hand up button. Oh, okay. It's taking his hand down. That's fine. One thing I will say about the Edison versus Tesla thing that you may or may not know. Actually, I wonder if I can find the video. I'll just see if I can find find this while I talk about it. So it actually got a little bit well, pretty rough between Edison and Tesla in regards to this idea of AC versus DC. So it was clear that I haven't read about this for a while, so forgive me if I'm a bit vague, but it was clear that whoever's idea took precedence was going to earn a lot of money of future earnings in the electrical industry, I suppose. So they did some pretty strange shit to try and disprove each other, and specifically Edison. So if you think about it, I guess another way to look at it would be Edison was kind of like the Apple of the day, whereas Tesla was maybe Elon Musk or Android or something like that. So one was the big powerful one who was pretty ruthless, and the other one was the underdog who had some good ideas but kept getting smacked down. So I don't know if anyone's heard of this. Let me see if I can share a video. Will this work? Okay, you're gonna can you guys see my screen? Are you seeing the video here? Okay, so look away if you're sensitive. This is a very old footage. Obviously, it's from 1903. So in order to prove that AC was a terrible idea and that DC was better, the experiment was bullshit, by the way. But in order to prove that, the Edison company connected a high voltage AC supply to an elephant. Is that better? That's full screen now. There you go. Yeah, really, really look away if you are sensitive. Let's see that again. There's our elephant. Seems quite happy. Oh, it's gone all tense. Smoke coming from feet. You can see sparks and stuff at the feet as well. And elephant falls over dead. I agree, Rangi. That is crazy as shit, right? So this was the Edison company's idea to prove that AC was terrible because it was so dangerous. So this is like modern day Donald Trump shit, right? Or olden day Donald Trump shit. That like it's pure bullshit. There's no reason why AC is worse than DC. But they knew that people didn't know that. They knew that people didn't know that, and so they were able to construct this experiment that was perhaps technically correct. That yes, that AC's voltage is pretty dangerous because it killed an elephant. It doesn't mean that DC was any safer, and they probably weren't using the same AC voltage that you would use in your house or anything like that. There was just it was just pure bullshit. It was all designed for it was clickbait, I guess, and it scared the hell out of people. And they nearly AC Power was nearly stopped in its tracks because of this mad guy who would electrocute an elephant so he could make more money to get his ideas pushed ahead of the other guy's ideas, which is just miserable, right? But there you go. Thomas Edison electrocuted an elephant. What a goddamn lunatic. It's also interesting, I suppose, to note there that the disinformation and the madness that we see in the world today is not new. People have been doing it forever. And in fact, even I don't even think Donald Trump would kill an elephant to prove a point. So in some ways, you could say that in fact it was worse back then. Yeah, I can't quite get my head around that someone would electrocute an elephant to prove a point. That's pretty mental. Okay, all right. So like how comfortable are we feeling then about that idea of um, uh, those ratios transforming voltage up means current goes down, power on both sides of the transformer remain the same. Are we feeling pretty good about that? Cool. Okay, where are we at then? Let me just find a spot. Okay, you should be able to all see the slideshow again. What are we up to? Yeah, so here is our equation that includes voltage, number of turns, and current. So we can see that at the top we have primary voltage, primary turns, but secondary current. And then at the bottom, secondary voltage, secondary turns, and primary current, which means that if primary voltage or primary turns go up, then secondary current goes up. Primary current goes down. Yep, I think we've done a pretty good job of explaining that. All right, let's take a break for Smoko. We'll come back at 10:30. That slide that I've got up there has a calculation on it. Transformer is connected to a 200 volt AC supply. The primary winding has 500 turns. Secondary winding has 100 turns. A 10 ohm resistor is connected across the terminals of the secondary winding, how much current will flow in the primary winding. So given everything that we just gone through, we should be able to work that out. So either take a couple of minutes now or a couple of minutes before 10:30, work that one out. So be prepared with your answers at 10:30. Does anybody have any questions at this point? No, everyone's happy? Okay. So have a crack at working that out. We'll start back again at 10:30. Thank you. Okay, we're back. Have I got everybody? Or somebody? Cool. Okay, so if we had a crack at this, equation, anybody care to give us an answer? Four. It's the answer 4. So Tanner says 4, Jade says 4, Raymond says 0.05. So someone else is typing. Let's see what they got. Rangi got 4 as well. Shit, looks like you're outvoted, Ray. Let's see. Let's have a look. Okay, so just looking at the bare equation itself, we're seeing that transformer is connected to 200 volts AC. Primary winding is 500 turns, secondary has 100. So we've got a 5-to-1 ratio of turns from primary to secondary. A 10 ohm resistance is connected across the terminals of the secondary winding. Okay, so how much current will flow in the primary winding? Well, first we need to work out what's happening at the secondary side. You've got a 10 ohm resistor there. We have a turns ratio of 5-to-1 from primary to secondary, which means, according to those formulas we looked at previously, we have a 5-to-1 ratio of voltage. So if we have 200 volts coming in, that must mean we have 40 volts going out on the secondary side. 200 divided by 5, because it's 5-to-1 ratio, gives us 40 volts on the output. Is that right? Yep. Yep. So 40 volts on the output at 10 ohms means that the secondary current will be, that's simple Ohm's law, right? V equals IR. Our voltage is 40. Our resistance is 10. So our current must be 40 divided by 10 is 4 amps on the secondary side. But that is not the current on the primary side, which is what the question is asking for. How do we work the current on the primary side then? Well, if we know on the secondary side we have 40 volts and 4 amps, we can multiply those together to give us 160 watts is being consumed on the secondary side. And we know that the wattage doesn't change. So whatever the wattage is on the secondary side, it must be the same on the primary side. So to work out current on the primary then, we've got 160 watts and 200 volts. So power equals volts times amps, which means amps must be power divided by voltage. So if our power is 160 watts and we divide that by our input voltage, which was 200, that gives me a current of 0.8 amps. Let's have a look. Here it is here. Secondary voltage equals turns on the secondary divided by turns on the primary times primary voltage. That's our that's just our turns ratio multiplied by the primary voltage, which is what we did. 100 divided by 500 times 200 gives us 40 volts. Does everybody agree with that? Everyone's happy with 40 volts on the secondary? No, take your silence as agreement. Oh, yeah, Tana agrees. Okay, good. To work out secondary current then, I I on the secondary equals voltage on the secondary divided by resistance of the secondary. So that's just I equals V over R, simple. 40 volts divided by 10 ohms. We were told it was 10 ohms, gives us 4 amps. So those people who said 4, yes, you're correct. 4 amps on the secondary. However, the question said, what is the current on the primary, not the secondary? So you've only gone halfway. So half right. So we must continue then. And as I said, we work out what is the power consumed on the secondary side. We can work that out because we know the voltage and we know the current. 40 volts times 4 amps gives us 160 volt amps. Volt amps is just another way of saying watts in this equation. So 160 volt amps or 160 watts means the same thing. So we know if it's 160 volt amps or 160 watts on both sides, then our primary current must be the watts divided by volts, or 160 divided by 200, which gives us 800 milliamps or 0.8 amps. Did anyone get 0.8, or did we all just misunderstand the question? Oh, you did, but you didn't work out the wattage. You just used the other way to do it would be just use that turns ratio still. So it's 5 to 1. So if we know it's 4 amps on one side and it's a 5 to 1 ratio from primary to secondary, then the primary current must be 4 times less than the secondary current, which would be another way to get the 0.8 without using the power. Is that what you did, Solar? Yep. So either way works. Okay. Well, it seems like we've kind of got a handle on that. So those people who got 4, just remember primary and secondary, right? Secondary is the output side, primary is the input side. Cool. Are we happy with that? Does anyone feel confused by that equation? Okay, let's move right along. Auto transformers, right. So now we've spent a couple of hours just trying to get our head around what a transformer is and how it works. And now I'm just gonna throw it all out and we'll talk about auto transformers instead. So an auto transformer is a single continuous winding. So we've talked about double wound transformers, and normally when we talk about a transformer, we're talking about a double wound transformer. So it's two completely separate windings. In an auto transformer, we have a single winding, so that runs between phase and neutral, and then we're going to tap that winding at some point along it in order to give us a different voltage. We'll come to how that works in a second. So advantages of our auto transformer: it requires less copper because it's a single winding, simpler to construct because it's a single winding, less expensive to manufacture because it's a single winding, and it requires less space. I bet you can guess why. Because it's a single winding. So we only have one winding in an auto transformer. The disadvantages: cannot be used for isolating the two winding. So that's one of the features of a double wound transformer, is that there's a safety advantage because the two separate windings are isolated, and it's to do with earthing. We'll come back to it. But the auto transformer does not have those two separate windings, so we don't have that isolation. Incorrect polarity or open circuit on the common part of the winding will result in the full supply voltage appearing across the secondary terminals. I'll explain that when we get to the how it actually works. Oh, here it is here. So in this picture here, you can see we've got 230 volts on the input, and we've got 24 volts on the output. As I said, we have one single winding, so that's running from our phase to our neutral, and then we tap off the winding here in the middle to give us 24 volts on the output. And it's really simple. It works on exactly the same principle. All of the same equations and stuff apply. It works on the exact same principle, is that if I've got 230 volts across that whole winding and it was X amount of turns, then I just tap at a given number of turns to get whatever voltage I want. So in this case, if we had 230 volts applied and I had 230 turns, 230 coils, that would be my total, the main coil will have 1 volt per turn, 230 volts and 230 turns, which means if I counted 24 turns and tapped off at the 24th turn, then I'll get 24 volts. If I tapped off at 100 turns, I'll get 100 volts. Again, I'm just making up those numbers to make it simple, but it's exactly the same as the double wound in the sense that the ratio still applies. Ratio of primary turns, which is the whole winding, compared to secondary turns, which is just the piece that we're tapping off. And that will give us our reduced voltage. So in the second picture, you can see here where they've drawn the red X, and we have an open winding. If we don't have that continuous winding all the way through there, if we've broken it after the tapping of the secondary winding, that means we're going to see 230 volts across our secondary output rather than 24 volts, because we don't have, there's no continuity between the tap and the neutral inside the main winding. So there'll be no volt drop, and therefore 230 volts will be present, which is a massive hazard, and there are some really specific requirements for auto transformers that for this exact purpose, and one of them is that you cannot use an auto transformer for any child's toy. Back in the day, and I remember this actually, you know, the old slot car sets that you buy with the plastic track, and you put them together, and then you put your little car on there, and you have a controller with a trigger, and the cars zoom around. I know I'm showing my age, but I had one of those when I was a kid. Oh yeah, Bailey knows what I'm talking about. Good, at least somebody does. Yeah, so commonly they used to be supplied by a auto transformer, because we want it, yeah, Hot Wheels type thing. So we plug that transformer into the wall, and then we just use an auto transformer, which is simple and cheap, and then it gives us an voltage output to our track. The way that those cars used to work is that on the track itself, it had two little metal inserts, and when the car sat on there, you know, that supplied a voltage to the car between the two metal tracks, supplies a voltage to the car. If we get an open circuit in the secondary part of our auto transformer winding, then we're going to get 230 volts on that track, which will A, blow up my car, and B, give me a hell of a shock if I touch that thing. So that auto transformer might be bringing that voltage down from 230 out of the wall down to maybe 12 volts to power those little slot cars. But if I get a fault in my secondary winding, I'm going to get 230 volts on the track, and that'll kill some poor kid dead. 100% fry them. So there's actually a rule. It's written in the standards that you must not use an auto transformer to supply a child's toy. So auto transformers aren't used very often anymore, but they still exist. And there is that specific hazard with them. Now, in terms of the calculations, though, everything that remains the same. I know that might look or sound quite confusing because it doesn't look the same. It doesn't look like a double wound transformer, but you'll just have to believe me on this. When we use an auto transformer, when we're doing the calculations for an auto transformer, we're going to use the whole winding from top to bottom as the primary, and then the part between my tap and the neutral is my secondary. And I would consider those two windings separate windings, just like a double wound transformer. So there'll be a part of the windings that is common, but in terms of our calculations, we can treat them as separate. So here's a calculation here. Let's have a look. A transformer is connected to a 230 volt AC supply. The primary winding has 400 turns, and 87 of those turns are common to the secondary winding. A 20 ohm resistance is connected across the terminals of the secondary winding. How much current will flow in the common part of the winding? Okay, so let's break this down a little bit. 230 volts being supplied to 400 volt primary. It says 87 of those turns are common to the secondary, which means that I'm branching off 87 turns above the neutral. So that means that I can assume, I can do this calculation as if it was a two separate windings. One has 400 turns and one has 87. What do I want to work out? 20 ohm resistor across the terminals of the secondary. How much current will flow in the common part of the winding? So that's the bit of the winding that is shared by both the primary and the secondary. So our calculation remains the same. Secondary voltage will equal the turns on the secondary over turns on the primary. That's giving us our ratio multiplied by primary voltage. So our secondary turns are 87. Primary turns are 400 times the 230 volt input says that I will get 50 volts. 50 volts on our output. So my secondary current then would be secondary voltage divided by secondary resistance. That's just basic Ohm's law, V over R. So 50 volts divided by 20 ohms equals 2.5 amps, which means that my primary, the power on the secondary is going to be 125 volt amps or 125 watts. 50 volts times 2.5 amps, so 125 watts. And we know that the primary power and the secondary power must be the same. So our primary power will also be 125 volt amps. And here it is illustrated. So on the secondary side, if you look at where the tapping is coming out for the secondary to the load, we got 2.5 amps there, 20 ohms, 50 volts. $125 volt amps divided by 230 volts AC gives us a primary current of 543 milliamps, 0.543 amps. So that is flowing at the top there, along that conductor, through the winding, and then we have 2.5 amps going out to the load on the secondary. Now, you might rightly ask then, where's the rest of that current coming from? How do I get 2.5 amps on the secondary if I've only got 543 milliamps coming in on the primary? Well, this is where that transformer action comes in. It does not, it's not working like a circuit, just like a series or parallel circuit on a normal resistance. We have the transformer winding is inducing a voltage. It's a type of self-induction, which means that the shared current on the part of the winding that is both the secondary and the primary, the current in there must be 2.5 amps minus the 543 milliamps on the primary side, which means we have 1.957 amps flowing in the common part of the coil. Here's the equation here. Current on the primary equals the primary wattage divided by primary voltage, which is 125 volt amps divided by 230, 543 milliamps. So the common current then is the current on the secondary minus the current on the primary. 2.5 minus 0.543 equals 1.957 amps. I know that is a strange and difficult concept. This is still something that bugs me in my brain. Like, how do auto transformers work? Where does that extra current come from? It doesn't make any sense to me. The only way that it makes sense is if you assume that an auto transformer, in spite of being a single coil, is actually two different coils. They're two different coils, just like a a double wound transformer, and therefore that transformer ratio still applies from primary to secondary. So the next equation then, same deal, auto transformer. It's connected to 230 volts. And this time it says a 65% secondary tapping. So that means we're tapping off 65% of the primary winding as our secondary. So the input current is 30 amps. To calculate the output current and the secondary winding current. Or when it says secondary winding current, it's talking about that that current in the common part of the winding. So our secondary voltage then, if we got a 65% tap, we'll have 65% of the voltage. So it'd be the primary voltage times 65%, or 230 times 0.65, gives us 149.5 volts on the secondary. We know from our transformer ratio calculation that the current on the secondary divided by current on primary is equal to the voltage on the primary over the voltage on the secondary. So the secondary current will be primary voltage times primary current divided by secondary voltage. 230 times 30 divided by 149.5 equals 46.15 amps. 46.15 amps is the output to the load. So then our common current, well, we just saw that before, right? If our secondary current is higher than the primary current, then the common current must be secondary current minus primary current. So we have 46.15 amps output and 30 amps input. So the common current must be 46.15 minus 30. And here we have that here. Common winding current is secondary current minus primary current. 46.15 minus 30 equals 16.15 amps. Okay. How do we feel about that, team? Look, I know that's not easy. Even as I explain it, I feel like it feels like there's so much more stuff that's not being said there. But the reality is what we need is the calculations, not the in-depth understanding of how a auto transformer actually comes up with the numbers that it gets. What do you mean a lot? Like a lot of current or a lot of information? It is a lot of information. I agree. Yeah, it's a lot of steps. Look, that part of it, I think I'm pretty comfortable with that. I think you guys can pick that up pretty fast because all you need to understand is those, VP over VS equals NP over NS equals IS over IP. So if you can just hang on to that, and then you can substitute in the values that you need if you get any questions that look like that. But just checking now. Yeah, okay. So that auto transformer maths is not in the test. So I'm not going to spend heaps more time on it. In fact, the test for this one looks pretty straightforward. So whilst I know it's a lot of information, yeah, look, I don't think it's where you could sit here all day trying to figure it out. But just follow those formulas if you need to do that, and you should be fine. Okay. So next thing we want to look at is voltage regulation, and this is another way of saying efficiency, I guess. So we will always have a reduction in voltage from the primary to the secondary. Even if it was a 1-to-1 ratio, you will lose something in there. So this is called voltage regulation. It's the reduction of output voltage as a percentage of the full load voltage. The voltage regulation percentage is the secondary voltage at no load minus the secondary voltage at full load divided by the secondary voltage at full load. So what we're saying there is that if I plug in a transformer and I measure the secondary voltage, as I put a load on there, when I plug something into it, that voltage is going to come down a little bit. That would be because as we start to draw current, remember we're going to lose a little bit of in the iron core. The transformer is not 100% efficient. So the more current I draw on the secondary, the more it's going to slightly bring down that voltage. So this is just a concept that you need to know. Again, it's just a formula that you need to be able to look at and calculate that the secondary voltage, no load, so that's with nothing connected to it, minus the secondary voltage at full load divided by the secondary voltage at full load. So the full load voltage will be slightly less than the no load voltage. So here's an example here. If a transformer output voltage is 20 volts at no load and 16 volts at full load, what is the voltage regulation of this transformer? So 20 volts no load, 16 volts at full load. So we would go 20 minus 16 is 4 divided by 16. 4 divided by 16, which should give us, actually, let's have our whiteboard. Give us a second for that to load. Can I give another? Oh shit, that's neat. I can even zoom in and out. Okay, cool. I learn something new every day. Okay, let's just push that to the side and find a new spot. So our regulation percentage equals voltage at no load minus voltage at full load divided by voltage at full load. Which are equal, in this case, our voltage at no load was 20 volts. And our voltage at full load was 16. Divided by voltage at full load, which is 16. Let me just wrap that guy out. Which would be 4 over 16. Must be 0.25, right? 0.25 or 25%. Sorry about my terrible writing there. So our voltage regulation in that equation then is 25%. Okay, if you need to do this, like I said, none of this maths is in this test. There might be some of this maths in some of the later tests because we're going to do a few topics on transformers. But remember that everything that we're doing today is videoed, it's recorded, it'll be available on Teams, so you can always come back to this and work through those examples as you are working it out. Just leave that there so we can see that if we need to come back to it. How do I go back to my slideshow? How do I go back to the slideshow? This is very confusing. Oh, I'm lost. I'm a bit lost. I think I need to, I'll have to upload that slideshow again, I guess. Just have to skip forward to wherever we were. Okay, voltage regulation. There we go. All right, tap changing. Okay, so this is just a concept that we could take advantage of here. Due to voltage regulation of a transformer under load, that is that the voltage on the secondary will decrease slightly as we load it. It may be required that the output voltage of the transformer be stepped up to compensate for the reduction of output voltage. This compensation for voltage reduction is commonly performed by tap changing. And here we have a picture here. So you can see that in this picture, the primary winding is, what have we got? 4 turns, and then the secondary winding is 1, 2, 3, 4, 5, 6, 7 turns. And we got the little tap changer at the top. So over 4 turns, if we just assume each one of those bumps on our drawing is a turn, I have 4 turns on the input, 7 on the output. Or seven on the output as it is there. You can see that there is a 3-way switch, which is switched to the bottom terminal, which means that I'll have seven turns on my output. So if I loaded up that transformer and the voltage started to reduce, I could change the tap to the middle one and give myself an extra turn. So instead of having 4 on the input side and 7 on the output side, I have 4 on the input side and 8 on the output side. And we know that the basics of the turns ratio across a transformer tells us that if I have more turns on the secondary, my output voltage is going to increase. So this means that in this case, I had 3 options. So as that voltage declines through voltage regulation, through losses in the transformer, when I start loading it, then I could increase the number of turns by using that switch to give myself a slightly higher voltage output. Does that make sense? It's just a way to add more turns onto the secondary. Really, it's pretty straightforward. Yeah, okay. If Rangi understands, then everyone understands. All right, so some stuff about transformer ratings then. The winding of a transformer has a small amount of resistance. So we've talked about this in relation to, what were we talking about yesterday? Windings having a, when we're talking about the fluorescent lights, right? And we said that although if I put a multimeter on my ballast, it's going to give me a pretty low result, yeah, because it's just the resistance of the copper. But my actual load would be much higher because that would be the magnetism that's generated. And the transformer is no different to that because, again, it's just a coil, or in this case, 2 coils, where when a current flows or when a voltage is applied, rather, it creates a magnetic field. However, as current is flowing through the transformer, theoretically, the transformer is just transmitting power from one side to the other, right? So in theory, the transformer is 100% efficient. Whatever I put into it, I get out of it, at least from the perspective of power. I can change the voltage up and down, which means I can change the current up and down, but the power input and power output should be the same. But we know that that's not going to be true. Nothing is 100% efficient. And when current is flowing in the coil has some resistance, and therefore some heat will be generated just by current flowing through the copper. So that is what we call our I squared R loss. Now, if you remember back to when we did the power module ages ago, I squared R was one of the formulas for our calculation of power, like volts times amps, or R squared or V squared over R, or I squared R. So we call these our I squared R losses, otherwise known as copper losses. Power output of the transformer is limited by the temperature rise of the winding. So if you think about that formula I squared R, even if we have a relatively small resistance of the coil, for every amp that I put through it, as the current increases, then the amount of heat generated in the coil must increase, because that copper loss, that I squared R calculation, is going to continue to increase. If I had 1 ohm of resistance and I was putting 10 amps through it, then my power consumed in that coil, this is power consumed in the coil, not power used by the secondary circuit. The power consumed in that coil would be 10 ohms times 1 amp, right? Sorry, I squared R. So it would be 10 amps squared, 100 times the resistance, 10 ohm, 1 ohm. So that would be 100 watts. 100 watts of power is consumed just by the coil. And that, when we say 100 watts of power is being consumed, that's 100 watts of heating. So that transformer is going to start to heat up. And then we could see by that equation, if I continue to increase the current, that is, I'm putting more demand on the secondary side, and therefore more current is flowing in the primary. So if I increase the loading on the secondary so that now we've got 20 amps flowing through the primary, then my I squared R equation would become 20 squared times the resistance, 1 ohm. So that would be 400. That's 20 squared, 20 times 20 is 400, times the resistance, 1 ohm. So now I've got 400 watts of heating occurring inside my transformer, just because of the resistance of the copper in the windings. So therefore, we can see that as we increase the current, then the power consumption, or the copper losses, the I squared R losses in the transformer, are going to increase. The heat output of the transformer is going to increase. And so the power output of the transformer is limited by the temperature rise of the windings. We don't want to overheat the transformer. So that's going to be our limiting factor. So again, although we think about, that transformer is just transmitting power from one side to the other with a voltage change in the middle, there is some power consumption in there. There is some heat generated. Therefore, there is a limitation in how much power that it can transmit for us. It's the current in the windings that determine the heat. The transformer has a maximum current rating to keep the heating within the design limit. The current rating in the windings or the current in the windings is that's what determines the heat, because of exactly what we just said. I squared R is going to be the consumption of power inside the transformer itself. So for this reason, the output of the transformer is not given in watts. That's why we use volt amps. Because for a particular wattage, the current in the winding must increase when a reactive load lowers the power factor below unity. Unity power factor, we kind of briefly talked about power factor yesterday, but unity power factor means a power factor of 1, or an efficiency of 1. Every time I have an inductive load in a circuit, my power factor is going to decrease, my efficiency is going to decrease. Because the transformer is inherently an inductive load, it's magnetism, then we have less than unity power factor. So we're going to rate our transformer in volt amps or kilovolt amps, because wattage refers to purely resistive power, whereas we're going to have inductive components in this as well, and inductive power. So we call it voltamps. The formula is the same. We're just calling it voltamps, not watts. So this this diagram here just gives an illustration of how our power factor will affect our inputs and outputs. So on the left, we have a power factor of 0.98 or 98% efficiency. So with a 50 ohm resistor and a 10 ohm inductor at 0.98, will give us a power factor of 0.98, and therefore it's going to draw 4.5 amps from a 230 volt circuit, or 230 volt input voltage. If I have a 5 ohm resistor with a 15 ohm inductor, it's going to reduce my power factor down massively to 0.31, and we can see that the let me just check this on my calculator. I feel like something's missing here. Okay. There's some information here that we're not given, and that's to do with the inductive load. I think we're just going to skip this one, because this is unfortunately, team, this is not going to tell you anything that that is going to make any sense whatsoever, and I'm going to save any talk of power factor until we get to the unit on power factor. Unfortunately, the power factor stuff that we will do in module 7, that's probably the most complicated and difficult maths that we do. We're going to spend a lot of time on it and really get into it, but I'm not going to do that now. So we'll skip that. That's not in the test. So forget about that last slide. Don't worry about it. Okay, so transformer applications. For double wound transformers, gives us a step up and a step down of voltage and current. It gives us safety isolation. Like I said, the two coils are not connected together whatsoever. So we have an isolation from one side to the other, which means we can use this as a safety extra low voltage source. So we can have, say, a 12 volt output from a 230 volt input, which means that our output voltage is much lower, and it's much safer, and it's isolated. Okay, I'm just going to go back to whiteboard, and we're going to have a look at what that isolation means. We're going to see how good my drawing is. This will be my transformer, and here are my coils. Oh, good God. Close enough. And my transformer core. Okay. So I've got a phase running in to the top and a neutral on the bottom. And same on the other side. I have an earth wire connected to the body of the transformer, and of course that's going back to my switchboard. It's going to be connected to earth itself, via our earth stake in the switchboard, and it'll be connected earth to neutral, right? So if I come in contact, here's me, little stick figure. There I am. If I come in contact with the phase wire, because I am earthed, then there we go. This is my nice long arm touching the phase wire. Then we're going to have a current flow right through my body, through earth, down to the earth stake, back up through our earth wire, back to neutral. So now I've got a circuit illustrated by that wiggly blue line there. That's going down the phase, through my body, through earth to the earth stake, back up the earth wire to the neutral, and therefore I'm going to get a shock. Does that make sense so far? Everyone understands that, eh? We've seen this kind of example 100 times. Cool. Okay. So now we put me on the other side of the transformer. Here I am. And I guess because I'm on the ground, I am once again earthed. So in this case, I reach out and I touch the phase wire. What happens next? Anybody have an idea? Nobody wants to guess? Okay, well, the answer is nothing. Nothing happens because the current which would flow down through my body to earth doesn't go anywhere. There's no connection. Well, there's a connection from the earth back to the neutral on the primary side, but the neutral on my secondary is not connected to earth. We don't connect the earth on the secondary side of my transformer. So because the primary and the secondary are electrically isolated from each other, that means there's no actual circuit. I'm not connected to the neutral on the primary side. Well, actually, I am connected to the neutral on the primary side, but nothing on the secondary side of that transformer is connected to the neutral. And so this example here, our little stick figure man on the secondary side of our transformer will not get a shock. He is isolated from the, there is no connection to the neutral. There's no way for current to flow because there's no path back to neutral. Earth, the secondary neutral is not connected to earth, and therefore no shock hazard exists from phase to earth. Now, if our man was to touch the neutral at the same time, then he would get a shock. He's going to get a shock straight from phase to neutral. But on the secondary side of a double wound transformer, there is no connection from neutral to earth. Therefore, no shock hazard from phase to earth exists. So this is what we're talking about, safety isolation using a transformer. And when we do the practicals for transformers, we will be looking at an isolating transformer. We used to use isolating transformers before portable RCDs existed. So you could take your little transformer with you to a job site, plug that into the wall, and then you plug all your power tools on the output side of that transformer, and it removes any risk of getting a shock to earth. So it's a safety device, right? That's pretty amazing, right? Is everybody amazed? What's going on? I guess everyone must be amazed because you've gone completely silent. Just, I imagine you're all just sitting there with their mouth wide open going, wow, that's amazing. Okay, so that was one of the features of a double wound transformer, that safety isolation. Yeah, applications of auto transformer, reduced voltage motor starters. So it'd be able to start a motor at a lower voltage. This is helpful when we want to start at we don't want the full motor speed to come on straight away. I could use an auto transformer, maybe an auto transformer with multiple taps on it to slowly increase the voltage to my motor so that it's not trying to start at full speed. Auto transformers can be used for voltage regulation, so if I have, or variable voltage supplies. So again, by having different taps on my transformer, I can get different voltages. All right, regulations and rules. Sources of supply by separated extra low voltage or protected extra low voltage. So these would be extra low voltages that are supplied by the output of a transformer. So safety or protected extra low voltage means that it's isolated from the main source supply by using a double wound transformer, and the output of the transformer is extra low voltage. These are covered by clause 7.5.3 in ASNZS 3000, and that says source supplying SELV or PELV system shall be one of the following: a safety isolating transformer, a source of current independent of a higher voltage supply, such as an engine-driven generator or electrochemical source. So I can have a safety isolating transformer supplying my safety extra low voltage, or I could use a engine-driven generator because that's going to be separate from the main supply, or an electromechanical source such as a battery. So if I wanted a safety extra low voltage supply, I could use either of these options. Or I could use a source of current separated from a higher voltage electrical installation, such as a motor generator set, with electrically separated windings having a degree of electrical separation equivalent to that required by item A. This one here means that I could use a motor driving a generator. So I can have my motor supplied from the normal 230 volt supply, which then drives a generator, which gives me my low voltage, which is then obviously electrically separated because I've used a motor and a generator. So I'm electrically separated from mains supply. I can't imagine anyone would do that. It seems bizarre, but nevertheless, in the rules, I'm allowed to do that. So all we're talking about here is if I want a safety extra low voltage supply, how do I get it? What are the ways I can do it? And so those are the four methods. Now, by far the easiest one is going to be using a double wound transformer that's isolated from main supply and delivers a low voltage. One other alternative for my safety extra low voltage supply is certain electronic devices complying with the appropriate standards, where even in the case of an internal fault, the voltage at the output terminals cannot exceed extra low voltage. Higher voltage at the output terminals may be used provided that the voltage at the terminals is immediately reduced to extra low voltage if contact is made with live parts. Yeah, so what that says is I could use an electronic device or electronic supply to reduce my voltage from 230 volts down to safety extra low voltage, but it has to comply with the appropriate standards. This is not something that we need to worry about too much. We're going to buy something that either is safety extra low voltage or it is not. Such devices, so electronic devices, include insulation testing equipment, so like our insulation tester. The drop in voltage at any point in an extra low voltage electrical installation shall not exceed 10% of the nominal value when all live conductors are carrying the circuit operating current. So that's a reference to our maximum demand. So if I have a safety extra low voltage system with 12 volt output, then I need to make sure that when that system is carrying its rated current, that the voltage at no point on the output side of my transformer cannot be more than 10% drop. So the way I would get around this is just like with our maximum demand is using appropriately sized cables. A question there, why would electric toys such as a train set require a transformer? That's a good question, actually. Why would I use a transformer for an electric toy? Nobody cares to answer that one? Jade is typing. Let's see what Jade has to say. Yeah, to give a lower voltage, right? It's a fairly obvious answer. We don't want kids running around playing with train sets that have 230 volts on the tracks, right? So in that case, our train set is giving us that safety. Transformer is giving us that safety factor of changing the voltage down, and also giving us that isolation, so there's no longer a shock hazard. I could have 12 volts across the two tracks of a train set, and neither of those are going to give me a shock hazard to earth because I'm supplying it via a transformer, which isolates, and we've reduced that voltage way down, so it's way less dangerous. The electrical equipment. This is clause 4.14.3. Electrical equipment may be connected to an isolating transformer in accordance with clause 7.4. 7.4 is the one we just looked at. Safety extra low voltage supplies. Transformer efficiency. A transformer under normal operating conditions has inefficiencies in the form of iron losses due to the hysteresis properties of the steel core and copper losses due to the power being dissipated as heat in the winding. And we have touched on both of these. Now, iron losses are the current that is circulating in the core, which is of no value to us whatsoever. It doesn't give us any use, but it happens. That core is going to act like an iron core like we want it to, but it's in a way it's also going to act like it's a part of the transformer. It's going to act as a secondary coil, so some current will be induced in there, and that is wasted energy. Now, copper losses are, as we discussed, there's the wattage that would be burned just by the current flowing through the copper in the coil. Taking apart the magnetic load on the transformer, just the resistance of the copper due to that current flowing is going to cause some losses as well. So both of these things will affect the efficiency of our transformer, because that means that we're not going to get the same power out of the transformer as we're putting into it. So iron losses are constant. They're constant because that's just they're just due to the voltage induced into the iron core by putting a voltage onto the primary. So they'll always be the same. However, the copper losses increase with an increase in current squared, and I went through this earlier, that for a given resistance of that copper coil, as I increase the current, then the power consumed or the power burned there, and therefore heat output is going to increase. So as the current drawn by my load increases, so the copper losses in the transformer will also increase. The equation for calculating transformer efficiency is power output, so that's our usable power that we're getting out, divided by the power output plus the copper losses, the power, so the Cu stands for copper there, power consumed by the copper, and then power Fe being iron, so that's our iron losses. So our efficiency is our power output divided by power output plus power plus copper losses plus iron losses. If you think of that another way, you'll see that my power input required to get a given output power will be the output power plus the losses. That's how much I need to put in to get a given output. So that's what all this is saying, is that the efficiency is power out divided by power in, which is the same as efficiency for anything. So our power input is going to be the output power plus the copper losses plus the iron losses. And cooling. Okay, final thing here. So we've seen that our transformer is limited in terms of its power dissipation by the heat generated inside the windings. So in a large transformer, if we're talking about power transmission transformers, right, like the type that is changing our power line voltage down to the voltage you need at your house, we want those to be as efficient as possible. And so we want to reduce the heat as much as we can. So we could use various methods here. We could use air cooling, use oil immersion, forced air blast, or forced air circulation. So air cooling will look like the radiator of a car or something like that. Often you'll have fins on the outside of your transformer, or like a heatsink type aluminium or copper fins. Just allow air circulation around the transformer, and it's going to radiate out the heat. So that would be the first two there, air cooling or forced air blast. Forced air blast is going to be the same thing, except we're going to use a fan to push air over the transformer to cool it. Now, oil immersion or forced air circulation, this is pretty common with large transformers. So you have the transformer casing, a big square box. You see these everywhere, right? So as you drive around, you're going to see, now that I've pointed it out, if you haven't seen them before, street corners and stuff, you see big green boxes. I reckon they're painted green because it just blends in with the rest of the world. So they're a little bit camouflaged. But if you see these big green boxes on street corners, they're probably transformers. So you have the big green box. Inside there, we're going to have our coils. But now, rather than just sitting those coils in air, we're going to fill that casing up with the oil, and we're going to insert the transformer into the oil. So the transformer coils are actually sitting in oil. The oil will be an insulator, so that aids in insulation of our transformer, but it also acts as a cooling agent. So that oil flowing around the transformer windings is a better conductor of heat than just air. So that oil will help to cool the transformer windings and therefore minimize our losses. And then forced air oil circulation is the same thing. It's just that we're going to have some sort of pump or something to pump that oil around inside the transformer to increase the cooling effect, just like if we were using a fan for air cooling. And that's the end. Oof. Okay. That's that topic done. Now, I'm aware that your head is probably spinning a little bit after that one. There's a lot of information in there, and maybe actually that PowerPoint needs a bit of a rewrite, because I think there's probably more in there than we need. The test itself is far simpler than all the stuff that was in that PowerPoint. If you did manage to follow along and understand everything, well done, kudos to you. If you're sitting there scratching your head a little bit thinking, I feel like I only figured out half of that, don't worry about it too much. Once you get to the test, you'll see that the information that you need there is not as much as we were given. And then as we progress through this, I think we've got maybe 6 topics that are focusing around transformers from different aspects. These things will start to become a little bit more clear. So don't freak out if you didn't understand all of that. And as you probably noticed, I skipped through a little bit of it and kind of glossed over some of the answers because I didn't want to go into too much depth and confuse people even more. So the stuff where I've glossed over it, don't freak out about that. We'll either pick that up later, or it's not something that's super important. So with that said, do we have any questions at this point on the topic that we have just covered? No? Is everybody happy? Got a couple of people typing there, so I'll wait for them. So I have unlocked the test for this one. Now, as I said yesterday, because we're doing extra theory day this week, I don't expect everyone to get through all of those tests. So this topic and the next one that we'll do after lunch, I've put the due dates on those ones as the end of next week. So there'll be a due date on all of our tests for this week of the end of the week. So it'll be midnight on Sunday. But the 2 tests for today's topics still won't be due until the end of next week, because they're technically next week's topics. We're just doing them a bit early. So you say there, the maths is hard. Don't lie to me. Don't lie to me. So I know you got a good handle on the maths, mate. You'll be fine. But there's no maths in the test for this topic anyway, so don't freak out about it. Yeah, so you're more than welcome to have a crack at those tests. But remember, the ones that we've done for the Monday, Tuesday this week are due this week. The ones that we're doing today won't be due until next week. Cool. All right, shall we stop there then? Let's come back at 1:45. Go and have a break, have something to eat, jump into those tests if you want to, and we will do the next topic, 3-phase transformers, which is a little bit shorter than that one. So we'll start that at 1:45. Cool. See you then.